Hello, this is Maria Grandoli, Christina Valencia, Diana Nguyen, and Peggy Kuo, otherwise known as Team Too Legit to Quit. We believe there's more to students than just their test scores. In this video, we will be exploring a topic in California education. More specifically, we'll be analyzing the relationship between API scores and student body characteristics. Because of the Public Schools Accountability Act, California education now has the STAR, CAT, and CASE as standardized testing. The PSAA also developed API scores to measure a school's academic performance. API stands for Academic Performance Index, and its scores range from 200 to 1,000. It is calculated from students' test scores, GPA, and many other factors. We're interested in seeing whether there are certain characteristics about the student body that are good predictors for their school's API scores. In this study, we'll be looking at data from 2012. We excluded data from special schools, such as continuation, private, or special education schools, because we believe results will be more accurate if only analyzing an average public school. We examined the data of over 1,200 public high schools in California, and we hypothesized that certain social factors will have a significant impact on API scores.
So now we're moving on to the data exploration portion of our video. And our data was subsetted to only include schools that had a larger student body of at least 99 valid testing scores, because there's probably a greater variation in the data for smaller schools. Our predictors include number of socioeconomically disadvantaged students, or SD students, percent of English learners, percent of students with disabilities, percent of students in gifted and talented education, otherwise known as GATE, percent of Asian students, average parent education, and English learner significant. When we take a look at the box plot, we can see that between the scores 200 to 1,000, the average score that schools receive is 758.6. In addition, the number of socioeconomically disadvantaged students has the widest range with a mean of 554.4. We can see that there are many outliers in the data. As for the percent of English learner, percent of students with disabilities, percent of GATE students, and percent of Asian students, the data appears to be fairly similar with a mean between 7.7 to 9.1%. The average parent's education level is 2.73 years, and it appears that 924 schools out of 1,248 have a significant number of English learners. The correlation summary indicates that percent English learner and average parent's education level have the highest correlation with API. And looking at the pairwise correlation, it seems that the variables are linearly related to API. However, because of the dispersed cloud of points, there is a high variance for each predictor. So when we take a look at our graphical summaries, in SD students versus API, we see that there is a greater variability in API scores when the number of SD students are low. With increased numbers of SD students, range of API scores decreases. For percent English learner versus API, there is a general negative linear trend. For percent Asian students versus API, there is a general upward trend. Again, there is a high variability in API scores when the percent of Asian students is low. For parents' education level versus API, there is also an upward trend. On the other hand, the percent of students with disabilities versus API has a negative trend. The percent of students in GATE versus API has a similar outcome with that of Asians, and there is a general positive trend. Finally, for English learner significant versus API, we see that the range of API scores is similar for both.
Okay, so now we're getting into the data analysis. In order to choose the best model for our regression, we decided to do a backward and forward stepwise model selection process that would minimize Mallow CP and BIC while also maximizing adjusted R-squared. In the plots, a black box means that the corresponding predictor was included in that model, and a white box means that the predictor was not included. Doing backward stepwise selection, the model that maximized adjusted R-squared was a full model. We also see that the full model minimizes Mallow CP and BIC. We will now look at the model that forward stepwise selection chose to be as best. Looking at the forward stepwise plots, we see that the full model was also chosen to be the best model, since it maximized adjusted R-squared and minimized Mallow CP and BIC. So our backwards and forwards model selection both chose the full model to be the best choice for the multiple linear regression. In order to continue with the regression, we must first do a diagnostic plot check to make sure that the assumptions of linear regression are met. Looking at the residuals versus fitted plot, we see a random cloud of points centered around 0. This suggests that our error term has a constant variance and does not suffer from heteroscedasticity. This plot also suggests that there is a linear relationship between our predictors and response variable. Looking at the normal QQ plot, we see that the points fall fairly close to the normal line, except for around the tails. This suggests our error term is normally distributed around 0. Looking at the residuals versus leverage plot, we see that there are 3 potential bad outliers that have high leverages and high standardized residuals. Based on the diagnostic plots, we see that our assumptions for linear regression are met. So, looking at the top, we have our full model. In the model output, we see that all of our predictors are statistically significant. Therefore, all of them have a good ability to predict and explain the variability in API scores. Our model produces an R-squared of 64.5%, meaning that 64.5% of the variability in API scores can be explained by the predictors in our model. Also, we were not able to fit the VIF plots, but when we ran code to determine the variance inflation factors for each of our predictors, we got values that were below 5, which means that we do not suffer from the problem of multicollinearity.
So based on our data, we would like to revisit our hypothesis. So first of all, we did believe that higher numbers of socioeconomically disadvantaged students, English learners, and students with disabilities would on average result in lower API scores. Our second hypothesis states that higher number of students in the GATE program, higher percentages of Asian students, and higher average parent education levels would on average result in higher API scores. Based on our data analysis, we were able to accept both hypotheses. However, it was interesting to discover that we were incorrect in hypothesizing that a greater number of SD students was actually not indicative of lower API scores. Instead, for each additional SD student, we would expect on average a 0.008 point increase in a school's API score. To improve our analysis, we could have considered computing standardized coefficients, meaning that we would have a better understanding of the importance that each predictor played in predicting API scores, which meant we could see which variable had more weight on API scores. Furthermore, we could focus on using other sets of predictors such as other racial groups, more specifically looking at Blacks, Hispanics, or Caucasians. Also, in the future, we could also choose to subset the data differently by looking at elementary schools, or even middle schools at least. Lastly, it would be even more interesting to run a similar analysis for schools in European countries to see what the important predictors that contribute to academic performance on an international scale. Overall, this project allowed us to see that there is definitely more to a student's academic performance than his or her grades and test scores. The social, ethnic, and economical aspects of the student's background and what a school can offer to their students play significant roles, which could provide insight on how to reform and better California's education system.
Thank you for watching. Have a great summer.